Hi, my name is Jens and this is a video tutorial on snappyHexMesh. You're going to learn how to configure snappyHexMesh to mesh your first geometry. For this basic tutorial, we're going to mesh the propeller of a ship, which can then later be used to simulate the propeller in open water conditions. As geometry, we are using the KVLCC2 propeller, which was part of the Gothenburg 2010 CFD workshop and could be downloaded from their website. This website is not available anymore, and in order to provide you guys the opportunity to download a properly formatted STL file, we are hosting such an STL surface file on our website, and you can download the file from this website. Just follow the download link in the video description. Step 1 of this tutorial contains several preparational tasks, such as downloading the geometry from our website and creating an OpenFOAM case that we can work in. I assume that you are familiar with the Linux command line and know how to copy files from A to B. If this is not the case, please have a look at various online tutorials that teach you this stuff before proceeding with this tutorial.
The first step is to download the geometry from our website. I simply type in the address into the address bar of my browser and hit enter. You can of course use the link in the video description. We just have to wait for the download to finish, and I'm fast forwarding the video while this is downloading.
Once the download is finished, I move the downloaded file to my desktop so I can find it later on. In my case, Safari has already extracted the archive and I don't need to do it by hand. You might have to do it though, depending on your operating system.
After this preparation, I open up a terminal and jump into my run directory, which is simply done by entering run and hitting enter. I copy a tutorial that is already present in the OpenFOAM distribution so that I don't have to recreate the entire case structure manually. As template, I select the motorbike tutorial from the OpenFOAM tutorials. In the tutorials directory, it is located under Mesh, snappyHexMesh, and then motorbike. This tutorial can be copied from the command line using the rather longish copy command that is shown. Please note that I changed the target directory from the current working directory, which would be a dot, to snappy tutorial. Once the tutorial has been created, we change into the snappy tutorial directory that has just been created by the copy command. In order to keep the case directory clean and tidy, it is strongly advised to remove the old and now obsolete motorbike geometry from the constant tri-surface directory. The next step is to copy the propeller geometry from the desktop into the constant tri-surface directory so snappyHexMesh can find it later on.
After this preparation has been finished, we can now proceed with the tutorial and the first significant step of it, which is step 2, creating the background mesh. The background mesh for snappyHexMesh has to consist of only hexahedral cells. This is due to the fact that snappyHexMesh is built upon a data structure that is called octree. An octree is a tree that has 8 leaves. Hence, only hexahedral cells can be used for the refinements, but we will talk about this later on in detail. Just keep in mind, you have to have a mesh that has hexahedral cells only. You can't use a tet mesh or polyhedral cell mesh. This is not possible. You have to use a hexahedral mesh. In OpenFOAM we can create these grids using block mesh, for instance, and this is what we are going to do in the following. For the course of this tutorial, I assume that you are familiar with the working principles of block mesh. If not, please make yourself familiar with it. Either consult the user guide or various online tutorials or resources, or the OpenFOAM Technology Primer if you want or already have a copy of the book. Otherwise you'll end up just copy pasting entries of the dictionary we are going to edit without knowing what you are doing. So, what's the deal with the background mesh? The deal is that we are not going to create a very complex and sophisticated background mesh using block mesh, because creating complex and sophisticated block mesh grids is a very tedious and time-consuming and very nerve-wracking task, and we're not going to do this, at least not on video. We are going to create the most simplistic block mesh that you can think of. It's just one single big block where we are going to put the propeller inside. In order to fit the propeller into the background mesh easily, without having to move either the propeller itself or the background mesh, we need two very important parameters of the propeller. The first one is the propeller's diameter, and the second one is the propeller's origin. Both can be found using either ParaView or the OpenFOAM native tool SurfaceCheck. We're not going to use ParaView in this instance, but we're going to use the tool SurfaceCheck. SurfaceCheck itself is somewhat similar to CheckMesh, but it doesn't work on the volume mesh as CheckMesh does, but it works on the surface meshes. This means it can check, for instance, an STL surface for A, arrows, and B, it can put out the origin and the bounding box, for instance, to screen. Using the tool SurfaceCheck is quite straightforward actually. You just have to type into your terminal the tool name, which is SurfaceCheck, followed by the path to the surface file you would like to check, which is in this case constant tri-surface prop.stl. This fires up the tool SurfaceCheck, of course, which checks the surface for arrows and quality, and also prints the bounding box to screen. This may take some seconds, but once the program has finished, we can scroll up and look for the bounding box and estimate the propeller diameter from that value. The relevant lines of the SurfaceCheck tool output start with bounding box and are followed by 2 points. The first one is the minimum point of the bounding box, and the second one is the maximum point of the bounding box. From these 2 points we can estimate both the origin of the propeller as well as the diameter of the propeller. From this output of SurfaceCheck, you can see that the propeller's origin is located approximately at 0, 0, 0, which is very convenient for the mesh generation using block mesh later on. And you can also see that the propeller's diameter can be approximated to be 0.202 meters, which we are going to round to 0.2 meters just for convenience. So, how are we going to lay out the block mesh? The propeller, with its origin being at 0, 0, 0, is going to be located in the origin of the block mesh as well. The propeller's diameter is 0.2 meters, which is indicated by D dash. D is the original unrounded diameter that we estimated from the output of SurfaceCheck. The distance between the propeller's origin and the boundary with the lowest x value, which is called x min, is going to be 2d dash. Similarly, we are going to have a distance of 4d dash between the origin of the propeller and the boundary with the highest x value, which is going to be called x max. The remaining outer boundaries will have a distance between the respective outer boundary and the origin in the respective direction of just 1d dash. Of course, this is way too small for a proper simulation, but this tutorial solely describes how to mesh things and not how to simulate the propeller properly. Since we based our case on the motorbike tutorial, we have to delete some of the remainers from this tutorial in order to start from scratch. Hence, we open up the constant polymesh block mesh dict in an editor. I'm using Vim in this case, but you can use any editor you like. Just remove everything that's inside the following lists: vertices, blocks, boundaries or patches depending on your version, and edges, so that those 4 lists are empty and we can start from scratch. After the block mesh dict has been cleaned up, I'm going to add the vertices for our case right now. If you would like to skip this step because it's tedious and time consuming and error prone, you can just download the completely configured case from the video description and skip this step. After these 8 vertices have been added to the block mesh dict, it is a fairly straightforward task to add all of them to one big block in the block mesh dict. If you don't know how this is going to work, please confer, for instance, the user's guide or the OpenFOAM technology primer, where we have described this process in great detail. After the vertices and the blocks entry, the next entry in the block mesh dict that has to be defined is the boundary or patches entry, depending on the OpenFOAM version you are running. We are going to ignore this completely and leave this blank. This saves some space and some typing, and we can proceed with the actual snappyHexMesh tutorial. What happens when we are executing blockmesh is that blockmesh will automatically assign all those auto boundaries that are undefined to the patch that's called default patches. So we can later address all of them using the default patches name, and we can proceed with the snappyHexMesh tutorial right now. After these editing steps, please save and close the blockmesh dict in your editor, switch back to your terminal and execute blockmesh. This will create the mesh that is defined by blockmesh and save it in constant polymesh. A popular mistake that people usually do when they are new to snappyHexMesh is to have a background mesh that doesn't fit the geometry. This means that the background mesh isn't big enough for the geometry or is way too small for the geometry, and then the outcome of snappyHexMesh just looks very funny. And this is where we are going to check our background mesh and our geometry and their relation to each other in order to prevent ourselves from running into this trap. In order to perform this check, please open either ParaView or ParaFoam or whatever post-processing application you're usually using. I'm always using ParaView with a native OpenFOAM reader. This reader has the requirement though that there is a file present in the OpenFOAM case directory that you're trying to open, which ends on foam with small letters. This file is of course not present in the motorbike tutorial case that we have copied, and I have to create it. I always create those files using the touch command. Once ParaView has started, just click Apply to load the current OpenFOAM case, and then in order to load the STL geometry, click on File, Open, and then navigate to constant trisurface prop.stl. After this you have to hit Apply again, which then loads the STL surface. Once both the geometry and the background mesh have been loaded into ParaView, I'm assigning different surface representations to both of them. I'm using surface with edges for the geometry, which is in this case the propeller, and for the background mesh I'm either using the bounding box representation or the wireframe representation. In this case we haven't made any mistakes. The propeller geometry is aligned perfectly inside the background mesh, and we can proceed with the snappyHexMesh tutorial, which takes us to step 3, setting up the snappyHexMesh dict. The snappyHexMesh dictionary is located in the system directory of the OpenFOAM case that we have copied from the tutorials directory. Similar to the blockmesh dict, we have to perform some cleaning up actions on this dictionary as well, in order to get rid of the obsolete entries that are still present there and relate to the motorbike tutorial. Please open the system snappyHexMesh dict with an editor of your choice and delete all those entries that relate to the motorbike tutorial. Of course, this is tedious and time-consuming work, and most likely you'll forget some of those entries. If you want to just speed things up, you can still download the case and just proceed with the snappyHexMesh dict that is present in this case directory. So, how does snappyHexMesh work? It's impossible to describe the working principles of snappyHexMesh in 2 sentences. I'm trying to compress everything as much as possible in this video tutorial. From a user's perspective, snappyHexMesh is built upon the so-called refinement level. This is a scalar value that is defined on a per cell basis. Whenever a cell gets refined, this scalar value gets increased by 1. But what does this refinement level do to the mesh? Let's consider the most simplistic mesh we can think of, a unicube with one single cell. If we are refining this single cell by the level 1, the result will be 8 cells. This is due to the fact that snappyHexMesh is built upon the data structure octree. We have mentioned this earlier. An octree is a tree that always has 8 leaves. There's no way around it, hence it is impossible, even with some hacking, to make snappyHexMesh refine cells in just one direction internally. There are ways of circumventing this, but it's impossible to do this inside snappyHexMesh. snappyHexMesh performs 3 major steps, and we are going through each of those steps in the following. The first step is the castellated mesh step. This step takes the background mesh, reads it to memory, and opens all of the geometries that are created. And depending on where you have defined your location and mesh point, the points outside of the mesh are removed from the mesh, and all of the refinements are applied. This means that depending on your definition for the surface and refinement regions, you get really a lot of cells in certain regions. Later on, you won't be able to add any more refinements. All this has to happen now. When this step is finished, the resulting mesh is purely hexahedral, purely orthogonal, and looks somewhat like a Mexican Inca pyramid. As for the surface refinements, you basically have just 2 major options. The first option are the surface refinements. Surface refinements just refine the cells that are cut by the surface and those cells in the really near vicinity of it. So if you desire a surface refinement level of 4, this refinement level degenerates really rapidly with increasing distance to the surface. On the other hand, you do have the option to use refinement regions, where you can use any geometry and define different levels for different distances from this surface. Those distances can be either pointing outwards of the geometry, inside, or in both directions. This has the most versatile options and is usually used to refine certain regions in a mesh without removing the cells. If you are using the surface refinements though, the cells inside your geometry or inside and outside of your mesh are removed. It is this step that requires the least amount of user interaction from all of the 3 steps. Only some iterations have to be defined by the user, and once some working settings for this very problem have been found, they are usually not changed too much anymore. This step takes the volume mesh and the geometry, which is represented by a surface mesh, and snaps the boundary points to the surface mesh. In order to do so and still retain a properly defined mesh with no negative volumes and a high quality mesh, some points may have to be introduced or removed from the mesh. This entire process is a very iterative process, which is why those iterators have to be defined by the user in the snap controls dict. The last step of snappyHexMesh is the step where the boundary layers are applied. It is called add layers. Those layers are usually made out of prisms, which are extracted from the surface. So the boundary points are moved from the boundary into the mesh by those newly introduced volume cells. The number of extracted boundary layers are defined on a per surface basis. So if I consider a cube, that is my geometry, that has 6 different surfaces, I can define 6 different boundary layer numbers for each of those surfaces of the cube. Similar to any other mesh generator, it is possible to define the way those layers are extruded from the surface based on various parameters. Those parameters include something like the minimum thickness of the first layer and the maximum thickness of the last layer that are applied to the surface. Some parameters account for the curvature of the geometry, which limits the addition of those layers. And you can also switch between absolute and relative dimensionings for those layer applications. The specifics of how the snappyHexMesh dict will be configured for the propeller case we are currently working on, and how snappyHexMesh will be executed, will be covered in the second part of this tutorial. The second part will be published in a couple of weeks' time. Until then, I hope you have had some nice time and have learned something. If you like what you have seen, please subscribe to our new YouTube channel, and see you in a couple of weeks. Bye!